So normally maybe you have encountered diffraction before. So we have two openings. Sorry, we have one small opening. So this is these are my barriers, barrier, barrier, and then I have another barrier over here, barrier. So normally we have a plane wave. This is, I mean, these are the wave fronts of my wave. So at this particular point, the wave begins to become like this. So as you can see, your expectation is that, let's say I have a vertical line here, and then I have another vertical line. Your expectation should be, you should be seeing the wavefront like that, right? But in the actual case, we have the phenomena of diffraction. We have the diffraction phenomenon, so it spreads after it passes through the opening here. So this is the traveling direction, this one. So we should see a few light waves behind here. For example, if the entire thing, the entire surface here is the water wave, or the water, the seawater, then if you induce a plane wave, P-L-A-N-E, plane. Plane wave means just like the sinusoidal wave. So if you view from the top, you will see the wave fronts that looks like this. No? So if these wave fronts pass through the barrier over here, or the opening over here, then it will spread out. It will spread out like that. Okay. So this is the phenomenon of diffraction. So it is also possible to have this kind of phenomenon in light waves. So basically, we will talk about this. But of course, for the water wave, it is something that we can see with our own eyes. But now we have the light, so we have no idea whether the light itself is behaving this way. So in order to prove this, we should have an experiment. The experiment that I've shown you, that I've demonstrated to you just now. So I have a thin wire at the center. So, and then I have my laser light. So this is my laser beam. So it passes through the wire. So it passes through the wire, and then the diffraction pattern happens. But today we are not focusing at diffraction. I'm just telling you that the purpose of the final part of your study here is to understand diffraction. So before we go into diffraction, we have to learn about wave superposition. Wave superposition, or the interference. So you can use the two terms interchangeably. So you can either use the superposition of light or the interference of light. So of course, the superposition of light is something simple. You don't have to make it complicated. You just think of the water wave. Okay, you think of the water wave, and then you have two waves, and then they are combining together. So of course, I can show you by using the software that I have written in Visual Basic. Okay. So now I am demonstrating to you the wave superposition. So, okay. As you can see here, the dotted line represents, okay, the dotted line represents the resultant wave, okay? The dotted line represents, the green dotted line represents the resultant wave. After the addition of the yellow or the orange sinusoid and the blue sinusoid. So the orange sinusoid adds with the blue sinusoid, then they form the resultant wave, which is in the green dotted lines. For example, if I superimpose, I hope you can see the green. I hope you can see the orange dotted line as well as the blue sinusoid. Okay, so because I should have maximized it, but I didn't do it in my programming, so I forgot to do that, so it won't zoom. So it is just covering over here. So for example, you can see my red dot over here. So this is my red dot. It is indicating the position, the zero's position of my orange sinusoid. So if I move my slider over here, this is my slider, left, right, left, right. So if I move the orange sinusoid, I am actually incurring some phase difference. You know? So as you can see, the phase difference is due to the, it depends on my x-axis. If my x-axis is the time, then it is due to the timing difference. But now we are focusing on the phase difference due to the spatial shift. I'll show you later the meaning why. For example, I have me as a wave source, and then maybe your friends at the back there as a wave source as well. So the distance between us will induce, not induce, it will cause the phase difference, the spatial, S-P-A-T-I-A-L, not special, yeah? Spatial phase difference. If I say temporal if I say temporal phase shift, it means the difference in timing. Maybe I emit the wave first, and then after that, your friend emit the wave after that. So we have the timing difference. So that will incur the phase difference as well. So I would say it is the temporal. Temporal is related to the time. So temporal phase shift. And then we have another one, which is the spatial, S-P-A-T-I-A-L. Spatial means which is due to the space. For example, I'm here and your friend is at the back there. So we are not at the same place, no? So there is a distance between us. So that will incur the spatial phase shift. But the thing is, at the end of the day, you will combine the temporal and the spatial phase shifts together, forming the phi alone. So phi itself is equals to phi due to the temporal plus phi due to the spatial difference. For example, if I say temporal, so this is my time axis. So this is t at 12 p.m. Okay. At this moment, I emit a laser light. Okay, a laser light beam. So the beam looks like this. You know, the wave of the beam. So the vertical axis will be the electric field strength as a function of time. And then maybe I don't know, this is just a thought experiment, yeah, which is not something realistic. For example, at later time, maybe 1 p.m., and then we have another friend, which is emitting a red laser light over here. Okay, so as you can see here, there is a timing difference between two of them. So this is delta t. So my phase shift due to the timing difference is given by omega times delta t. Okay. Let's say I have another situation. For example, I have my friends over here, and then this is me over here, and then we are emitting the waves. Okay, so maybe my friend's wave is blue in color. Sorry for my jagged line. So and then my wave is in red color. So of course, the distance from here to here and the distance from this point to this point, okay, they are not necessarily the same. Maybe at some point we are standing at the same distance from point P. But most of the time, it is not definite, no? So for example, maybe he is over here, then maybe me is over here, maybe I'm over here, then our distance from point P might be different, no? So the idea is that the maximum will not really meet with the maximum, not necessarily. So it depends on the positioning. So the guy over here, the situation here, it is not due to the timing difference because both of us, we emit the laser light beam at the same time. Okay, at 12 p.m., me over here and my friend, which is S2, and my friends over here, we are emitting the light beam concurrently at the same time. Okay, But still, we have the phase different as well, because the distance from here to here is not the same with the distance from my friends towards point P. So let's say if I replace the variable over here, with x, so this is the x direction for my wave, and this is the x direction of my friend's wave over here, because the direction is towards this direction. I mean, x is not necessarily, this is x, this is y. So x is parallel to the direction of propagation, okay? I hope you guys are okay. So you don't confuse here. The x-axis is actually, it's not the Cartesian coordinate. It is basically in the same direction with the direction of propagation. Let's say if the wave is moving towards this direction, then the x-axis will be in that direction. For example, the wave is moving towards this direction, then x is towards this direction. So that's the idea. I hope you're not confused with that. So, but the thing is, let's say this is point P. Okay, this is me as number 2. This is my friend, which is as number 1. He is located here and me is located over here. So the distance from me, myself, which is towards point P, which is the distance from here to here, is smaller than the distance from my friends over here towards point P. And that will also incur the phase difference or the phase shift, which is due to the space. So that's why I'm saying that the phase shift due to the space or the spatial phase difference is given by k multiplied with delta x. So instead of having delta t over here, I'm having delta x over here. So I hope you are imaginative enough so that you can imagine this. Yeah? You need to use your imagination at the moment. But if you are not able to do so, I do have my own software which helps to visualize this. Okay, for example, we close this one for a while, and then I have my double slit experiment over here. So this is, okay, I hope you can relate this. So as you can see, okay, as you can see here, yeah, as you can see here, at this particular point, this is me, this is my friend, source number 1. Both of us are holding the laser pointer, and then we are going to emit the laser beam at the same time. So I'm using the red light beam, and my friend is using the blue light beam. So this is my friend, this is me over here. The entire space here is the spatial space. I mean the space. For example, maybe here is London, here is Alustar, I don't know, over here. So we are situated at the different places. So I'm emitting the laser light at the same time with my friends, because we are now focusing at the spatial phase shift. So now when my light wave arrives here, this is known as point P, okay? And then as you can see here, the blue dotted lines, this one, this is the maximum. This is the maximum, this is the maximum as well, this is the maximum. This is the maximum. Or the maximum. So this one is maximum. So this is the maximum of my light wave, my red laser light, maximum. So whenever I mention that the maximum meets with the maximum, meaning to say the blue line here and the red line here, they are next to each other. And then if I move, if I move my position, so now the maximums or the maxima are not next to each other. So I have my red light maximum over here and my blue light maximum over here. They are not next to each other. So meaning to say they will not hit at this point they will not hit at the same time or at the same location. The thing is, the guy here, the maximum of the red light will reach this point later than the blue light. Do you get the idea? So let's say if I move this even more, so the light will cancel off. So now, as you can see, the red maximum here begins to meet with the blue maximum. Okay, maximum meets with the maximum. Can you relate this? I hope it is imaginable. Can you really imagine this? Are you okay, guys? So we need to say, I need to zoom this. I'm not sure whether I can zoom this. So yeah, I hope that you understand what I'm saying here. So we need to say, at this point, the maximum of my blue light meets with the minimum of my red light, because the blue line over here, and then there is no line over here. So the region, the portion where there is no color or there is no line, it means that that it is the minimum of the wave. So for example, here is the maximum, minimum, maximum, minimum, maximum, minimum. So here, minimum of my blue light meets with the maximum of my blue light. So they will cancel off. Okay, they will cancel off. So I'll show you why they will cancel off. I open this again. So for example, now the position of my, so I have my orange curve, which is the orange light, and then I have my blue light, the blue sinusoid. So let's say if I put them together at the same place, so meaning to say the blue curve is on top of the orange curve, or vice versa. So meaning to say the maximum plus the maximum. So this is my so the line here is 0. So the amplitude of the blue curve plus the amplitude of my orange curve, so it will double. So that's why the resultant wave maximum is over here. Let's say if I change the position, if I move my orange curve forward for about half of lambda, so from this point to this point is 1 lambda. So I'm shifting my orange curve forward for half of lambda, 1/2 lambda. So this is half of lambda, yeah, in the middle here. So as you can see, the green curve is the resultant wave. So they cancel off. So the maximum is 1 plus with the minimum, which is -1. So 1 plus -1 is 0. So for example, if I choose a point over here, so this point 0.5 plus with the blue color, which is over here, I suppose, this point plus with this point, which is minus 0.5, then it is approximately 0. Let's say if I move this exactly at half of lambda, which I'm not able to do so because also the stepwise. I don't know how to say this. The movement of my slider here is discrete. It is not continuous. Okay, it is not continuous. If it is continuous, then it is possible for me to make the resultant wave to be 0. But now it is almost 0. As you see, the green curve over here, the green dotted lines, it is approximately 0 because the maximum meets with the minimum of one another. So I know I'm saying this many times because I just want to make sure that all of us understood this. So maybe the guy at the back there, I hope that you are able to follow me. Okay. And then if I move my curve further, which is about 1 lambda, okay, if I push my orange sinusoid forward, forward towards this direction, yeah, from left to the right. If I push it forward about 1 lambda, then you will see that my resultant wave is becoming maximum again. It will double the amplitude. If you see the green curve, So basically the formula is given by, the formula for this one is the wave function of, the formula is given by the wave function of my orange curve plus the wave function of my blue curve. So this is E green. So the green is, the green curve is the superposition of the two waves. It's the resultant wave due to the superposition of the orange curve and the blue curve. So this is it. You just need to add them. You do the algebraic sum. If you have even more, if you have many waves, okay, if I have, let's say if I have another one, or another one, another one, so you just add them together. You just add them algebraically. When I mention add them algebraically, it means it's just like 1 plus 1, 2 plus 3. When I mention to you add them vectorially, then you have to make sure the components, you have to add the components. Okay, so that's the idea. When I say algebraically, because of course our guy here, the vertical axis here is the electric field strength, which is a scalar value. The strength, I'm not mentioning about the electric field. The electric field is a vector which has a direction, but I'm talking about the strength, which is the modulus, or what we call that, the magnitude of my electric field, which is fluctuating. So I hope you get the idea. And then if I even push this forward, if I push this further forward, so you will see this. I'll give the software to you. I'll upload on my drive, and then you can download this at any time. But the thing is, your Windows will detect that the software here is malware, because Microsoft it doesn't recognize me as a certified developer. So you have to allow that. So trust me, I'm not creating any virus behind this. Okay. Even though it is possible, if I want to spoof your computer, maybe in front it shows you that I'm demonstrating the wave, but behind it, it is capturing all of your data in your computer. It is possible, but please trust me, okay? Trust me, okay? So this is it. And then let's go back to this one, okay? If you cannot remember the reason why you have the fringes, you just put your hand like this, and so it is basically the same with this one. So of course, I don't know how to, just do this and then you will remember that. So the idea is, okay, now let's do the experiment here. So over here, does the maximum of my blue light meets with the maximum of my red light? No, okay. So we'll just leave it as it is. Now it begins to touch the blue maximum. So let's put some indicator here, and then it will they will touch together, and then until this point. So at this point they begins to not sitting next to each other. So I think this is the final point. So okay. And then if I move further, then they begin to touch together. So from here until here, which is over here. So I'll just, okay, and then I'll move further. So the blue one, the blue one touches with the red one. So begin here. Not touching anymore, so until here, I suppose. Can you see this pattern? The maximum, minimum, the maximum, minimum, the maximum. So that's the reason why you see the fringes. I hope you get the idea, okay? So this is, I've created this so that it helps me to explain this. If I were to explain using my mouth, I don't think it is imaginable. So it depends on the individual. It depends on the individual. Let's say if you have a good imagination, you can imagine many things, okay? Then it is always possible to do that. If you are not an imaginable person, then you need this kind of simulation software to visualize it for you, okay? I hope you are okay. So that's it about the fringes. So, okay, now let's talk about the technical. So before we jump into the technical part, we need to know the meaning of coherence. In order, from zero, from bottom. Let me explain from the bottom. So meaning to say, the two light waves, in order to see the interference effect, in order to see the fringes that I've demonstrated to you just now, you need to have the coherent lights. So meaning to say, I have my friends over here, S1, and then me over here. Our light waves should be coherent, okay? They should have, these waves should have the same frequency so that we can observe the interference pattern. But the thing is, if those light waves are not having the same frequency, interference will happen, okay? Interference will happen. But we cannot see the effect. We cannot see the effect, right? Because there is the difference in timing. So, we need to say the wave coming from here, for example, the maximum of the wave coming from S1 will be arriving a bit later than this one. So, I don't know how to explain this. So, maybe if I have another wave which is higher in frequency, so if both waves are not having the same frequency, then the situation is like this: having interference, no interference; having interference, no interference, and that kind of change is happening at a very short time, such that your eyes cannot even see that. So that's the general idea. I won't go deeper because it will confuse you. But at the moment, let's just assume that the light waves coming from S1 and the light wave coming from S2, both of them have the same frequency, meaning to say they are coherent. So I have my x-axis over here, and then I have my source number 1 over here, and then source number 2 is over here. So when I draw this one, and this one, the situation here is two-dimensional, okay? Two-dimensional. But if I do this, the situation is one-dimensional. So, maybe you view from this position. This is your eye. So you're viewing from this position. No, from here. So this is S1 over here, and this is S2 over here. And then P might be over here. This is your point P. So light waves should be coming from here to here. Okay, and then I have my red. Both light waves are coherent. They have the same frequency, okay? We are talking about that situation. We are not talking the situation where the frequencies are not the same. You just focus your mind that the frequencies are the same. So, of course, the color of my line color over here, it doesn't mean that it is blue laser light. No, now they are having the same color, but I just want to differentiate between the two lines using the different colors. So just bear that in mind, okay? So if I view this from this position, then you will. I hope you can relate. I hope you can relate. So this is something like this. So my P is over here, this is my line. So the line here is this one. I hope you guys are okay with that. So if I draw my blue line, my blue wave coming from here, and then I draw my red wave over here. So meaning to say the distance from here to here is given by lambda, and the distance from here to here is given by lambda as well. So they are having the same frequency and wavelength. Okay. But the thing is, the position of both sources are different. So maybe this guy reaches 0 at this point P. This is point P, yeah? But the guy over here is almost negative amplitude, negative of the amplitude, almost. maybe the negative should be over here. So it is almost negative of the amplitude over here. So the value here plus the value here is given by the resultant wave. You know, the value here plus the value here is given by the value of the resultant wave at this particular position. This one add with this one, so it is still over here. Okay, because this is 0 plus something, so the resultant point is still here. So I hope you are okay. Okay, so the wave function of my first light wave is given by E naught E minus I omega t. Okay, of course we can write kx minus omega t, I kx minus omega t. So we should have plus over here. And then the second wave is given by E naught E I kx minus omega t, but it is starting at the different position. So I have my delta x over here. So you should have you should plus with phi. Okay, plus with phi. But the thing is, it is in front, so you have to minus. Yeah, my apologies. You have to minus. So because the guy is over here is in front of the first source, then you have to minus. Okay. So the resultant wave is given by E1 plus E2, the algebraic sum of both wave functions. So it is given by E naught E I kx minus omega t plus with E naught E I kx minus omega t minus phi, like that. Are you guys okay? So so we will not really bother with kx, right? We don't really bother in our analysis. We don't really modify the kx, so we can just use this. Instead of using this one, we can also write this as E prime equals to E naught negative I omega t plus I minus I omega t plus phi. Because I'm not going to bother with my kx. This is mathematics, yeah? Throughout my analysis, I will not modify kx and omega t because they are coherent. So I won't do any modification to my omega t and kx because they are coherent. So finally, you can simplify this into E minus I omega t 1 plus E negative I phi. Okay. Are you okay? Because this is you know, the guy over here, this one can also be written as E I omega t times I phi, like that. So I have this one inside here, and then I have this one. I've just pull this one and this one outside over here. So I'm left with this one. Theta. So this is the resultant wave. I hope you can relate this. So it is easy for you to use the exponential form to find the resultant wave rather than by using the cosine. So if you use cosine of A plus cosine of B, so this is for wave number 1, this is for wave number 2. I don't really remember the formula, so it's 2 cosine of A minus plus B over 2 sine of A minus B over 2. If I'm not mistaken, maybe here is negative, here is positive, so I don't really remember the formula. So you have to do something with this. So, but if you don't remember the formula, you just use the exponential form. This is something straightforward for me. I hope it is something straightforward for you as well. Because here, I'm ignoring kx, okay? I'm ignoring kx. I'm just leaving omega t. I'll give you the reason why I'm leaving omega t later. It has something to do with the intensity evaluation, so I need to have my time variable stays there, okay? So this one is coming, the guy over here, okay, the guy over here is for the blue light, and this one is for the red light, okay? So I add them together algebraically. So this is the final form of my wave. So if I rewrite this, we have E naught 1 plus E I phi times E I omega t. So it seems like I'm having the same form of my wave function. Initially we have this one, okay? If you look at this, we have this one, or this one, and then this one. So I have the same form, but now I have my modified amplitude. I hope you can relate this. So now I have my modified or superposition or the resultant amplitude. The resultant amplitude is a complex number, but in reality, the one that you are seeing using your eyes is the magnitude of the complex number. The magnitude of the complex number. Well, if you could remember the magnitude of a complex number, for example, if I have my complex number x plus y, I, then the magnitude is given by the square root of x squared plus y squared, right? How about the conjugate? The conjugate of this one is given by x minus yi. Or if I have my exponential form, for example, I have minus I phi, so the conjugate of this guy is given by E I phi. That's the mathematical formula. I won't dig into that, so you just need to remember this, okay?